Kinetics 1. Measuring rates of reaction. A chemical reaction rate. The rate of a chemical reaction is defined as the change in the concentration of a reactant or product per unit time. So it could be the rate equals the change in the concentration of reactant over time, or the rate can be the change in the concentration of product over time. Remember, the square brackets is concentration in moles per decimeter cubed, and we can calculate the change by the final value minus the initial value. The standard units for rate are moles per decimeter cubed per second, but we do sometimes use millimoles per decimeter cubed per second or moles per decimeter cubed per minute. Okay, let's do a bit of stoichiometry and reaction rates. The rate of change for one species in a reaction can be used to predict the rate of change for another. So here we've got an example of nitrogen monoxide reacting with oxygen to give us nitrogen dioxide. What is the rate of formation of nitrogen dioxide if its concentration changes from 3.2 times 10 to the minus 4 moles per decimeter cubed to 8.0 times 10 to the minus 4 moles per decimeter cubed in 4 minutes? Well, we have initial and final concentration and we've got time, so it's fairly straightforward. The rate will be the change in the concentration over time. We see that the final is 8.0 times 10 to the minus 4, so final minus initial concentration divided by 4 times 60. We're converting minutes into seconds to get our answer, so very straightforward. So we now know the rate of formation of this, but we want to know in the second part the rate of consumption of oxygen gas during the same time. And I bet you can guess what we do since it's stoichiometry. Of course, we use a conversion factor. So we know the rate per mole for nitrogen dioxide, so we've got to change that the rate per mole for oxygen, and we can use a conversion factor because you can see here we've got 1 mole of oxygen for every 2 moles of nitrogen dioxide being formed. So in the conversion factor, we're converting to the moles of oxygen, and so that would go on top, and just do the math to get your answer. Okay, another question. The total mass of the system for the reaction below changes from 120.55 grams to 118.93 grams in 3 minutes. The volume of HCl used is 200 centimeters cubed. So we've got calcium carbonate reacting with hydrochloric acid, giving us calcium chloride, carbon dioxide and water. We're going to calculate the mass of carbon dioxide released and the amount of carbon dioxide in moles. Well, you can see straight away that solid, aqueous, gas, liquid, we're just going to lose carbon dioxide to the atmosphere. And so the change in mass is to do with the amount of carbon dioxide lost. So the amount of carbon dioxide lost is the final minus the initial, or initial minus final, should I say. And we get the grams of carbon dioxide lost. And we can then convert grams of carbon dioxide using our conversion factor for the molar mass of carbon dioxide. Obviously we want to get moles, so moles will go on the top, and to give us the moles of carbon dioxide. Next, we're going to calculate the rate of the reaction in terms of moles of carbon dioxide produced per second. Well, we know that we have 3 minutes, so we know that it's 180 seconds. We want moles per second, so moles will go on the top, seconds will go on the bottom to give us our answer in moles per second. And finally, we're going to calculate the rate of reaction in terms of the concentration of HCl consumed per second. And we've got volume here, we've got moles per second, so we just need to include the volume that we have there in decimeter cubed. Do note that experimental rate values may or may not be in moles per decimeter cubed per second, and you can see there that's just moles per second. So we've got moles of HCl consumed is we have the 0.0368 moles of carbon dioxide, and we need to use a conversion factor. We've got 2 moles of HCl for every 1 mole of carbon dioxide, and so we now know the moles of HCl consumed. So we've got the mole down here, we've got the rate of change of HCl over time. But we need to convert our moles here into moles per decimeter cubed. We've got the volume here, so it's going to be moles, 0.0736 moles, divided by our volume, converted it to decimeter cubed. And then obviously we need that in per second, and so our concentration, moles per decimeter cubed there, divided by the time it took, which is 180 seconds, gives us our answer. The concentration of a reactant or product may be measured indirectly in experiments using other quantities that change as reactants are used up or products form. For example, in a reaction producing gases, we could measure the change in volume of gas over time. We could measure the change in total pressure over time, and we could measure the change in total mass over time. Open systems, for this mass one, it tends to just use carbon dioxide because it's quite heavy. Trying to do it with hydrogen gas would be too difficult. Your error would be too great because hydrogen is so light. Reactions involving a reactant or product with a colour. We measure the change in absorbance over time. A reactant or product will absorb light of a complementary colour. Reactions involving acids or bases, obviously we could use pH over time, change in pH. Reactions involving changes in ion concentrations. Ions conduct electricity, so we can measure the change in conductivity over time. And chemiluminescent reactions, we can just measure the change in light intensity, increasing or decreasing over time. Let's have a look at an example. We've got calcium carbonate with hydrochloric acid, giving us calcium chloride, water and carbon dioxide. What quantities or properties or values change as reactants are used up or products are formed? Well, we can see in A, the solid, solution, liquid, gas is produced. If a gas is produced, we could measure the change in volume of carbon dioxide over time. We can measure the rate of pressure over time if it's a closed system, or we can measure the change in total mass of the system, and that only works if it's an open system and the gas is being lost. For B, you can see that we could also look at the HCl. Acid concentration will decrease as the reaction goes on, and so we can measure the rate of change of pH over time. And this only works if the acid isn't in excess. Example 2, aluminium and copper chloride, giving us aluminium chloride and copper. So what could we look at this time? What's changing? What's being used up? Or what's being formed? Well, we've got this copper chloride here. Why is that highlighted? Well, because it's blue, and so we can use the fact that the reactants will be a blue solution and the product will be colourless. So we're going from a colour to a colourless solution, and so we can measure the rate and change of absorbance over time. What about B? We've got copper chloride and aluminium chloride highlighted. It may not be immediately apparent what you could do here. Well, if you count up the ions, we've got 3 copper ions and we've got 6 chloride ions here, so altogether we've got 9 ions. Over here we've got 2 aluminium ions and we've got 6 chloride ions, so altogether 8 ions. So we've got a different number of ions in the reactants compared to the products. And so conductivity will change over time. Do note this is a bit of a simplistic explanation, because conductivity also depends on the ion size and the charge. Finding the rate by graphical analysis. We'll have a graph here of concentration over time, and it's product concentration, it's going up. If it was a reactant, concentration over versus time be going down. So the slope of this will be the change in y, which is concentration, over the change in time here. So we've got the rate of change of product over time, which is what we want for rate. So the slope of this thing gives us the rate of the reaction. We find average rates of reaction when looking at these graphs more often than not. So if you want to calculate the average rate of this reaction, what would you do? Well, we've got the slope of the line, the average rate would be the slope of the line from the start of the reaction at 0 times 0 to the point where the reaction ends. So you've got to decide, when you're looking at this, imagine it was just this slope here and we didn't have the red and blue line. You have to think, whereabouts is this reaction stopping? And you can see the concentration is flat from where this green square is. And so we can say this is where it ends. And so this red line would be our average rate, or how we'd calculate the average rate. You put in the numbers and you can see that the change in y is 0.138 minus 0, and time is about 13 minus 0, and you can do the math. Obviously if we had units here, we'd put the units in. What would happen if you used the line from the start of the reaction here to the very end here? This blue line. What was the effect of the rate value? Have a think. Well, that's right, the slope is less steep, and so the rate would decrease. It's going to be lower than it should be. And that's why you've got to find the correct place where the reaction actually stopped. Instantaneous rate of reactions. Asks us here to calculate the instantaneous rate of the reaction at 6 seconds. Instantaneous rate is the rate at a given time during the reaction, so at a specific time. In this case, we want to know 6 seconds. You calculate the instantaneous rate. You calculate the instantaneous rate by working out the slope of the tangent line at a given time. And so you can see we've drawn in a tangent line with this purple line, it's a tangent at 6 seconds. And then you can use that purple line in the same way to find the slope of the thing. You do the maths, put in the change in y over the change in x, and you'll get your rate of reaction, which is the slope. Some people make the mistake of just using the coordinates of the data points at the indicated time. For example, somebody might go, it's at 6 seconds and it's about 0.12, so it must be 0.12 divided by 6. But there's no change there. Okay, so it can't be rate. So remember, make that tangent and use a purple pen if you have one. Initial rate of reaction. This time, the initial rate is the rate at the very start of the reaction, the instantaneous rate at time 0. Ideally it's found using the tangent line drawn at time 0 seconds. This is sometimes a bit more difficult to do, and so often you would use, you find the average rate over a very short period of time, a very short period of time interval at the start of the reaction, by finding the slope of the best fit for that interval. And you can see here, you want to use at least 3 data points, even though we've only used 2 here. Well, it includes 0, it's 3 data points. And then you just work out the slope for the first few data points to find that initial rate. Some more notes about data selection, rate determination. If longer time intervals are used to measure initial rate for different trials, be careful with your choice of interval. Let's have a think about this. I want to comment on the validity of using these time intervals to measure the initial rate of each reaction ABC. Let's say we're going to use 0 seconds to 5 seconds. You can see that between 0 and 5, this seems the initial slope here is kind of the same, so you could use this one with the squares, it would be okay. This one here, the green one, if we kind of follow this slope, you can see it's okay up to a point, but then look, it has definitely gone down here. So At 5 seconds it would be slightly inaccurate. Over here again you can see the initial slope goes, we continue there, and it is not at 5 seconds. So only one of these would be good. The other two would be kind of okay, but far from ideal. You'd probably want to have it further down. Conversely, using 0 seconds to 10 seconds would be awful, because as you can see, the reaction has stopped, most certainly for the blue one, at 5 seconds. And it's kind of, if it said overall reaction rate, it might be okay for this one, but you can see how far off it would be for the square one. You're looking right up here. And the green one, if it followed the slope of the initial rate of reaction, it actually goes way off up here somewhere, so you couldn't measure it. So it would be useless to try and use 0 seconds to 10 seconds. Okay, here's a practice question. First of all, you would look at this and you've got to kind of draw in the best fit curve for the reaction. And I've done this, and I did it with a pen rather than using a line to highlight that you do need to kind of be able to do these freehand if they're awkward and curved like this. Ideally you'd have kind of a nicer straight line in this, but this isn't how it shows it here. And so I've drawn one in for question 1. You can see I would have been better suited to change to a ruler here to draw a nice straight line there, but I didn't, because that's how I roll. But you should not. You should have used a ruler. Question 2, use the graph to find the overall average rate of reaction. So first of all, we need to find where we think this reaction is ending. Where is it flattening out? Where's the concentration not changing anymore? And I'd say it was probably around here. Okay, around about 20 seconds, you can see it starts just getting flat. And if I had used a ruler, it would have stayed exactly on this line at 70. Okay, and that's why you should use a ruler. So we can look at the change for the concentration, which is obviously 70. We're going to plug it in to our slope to find the rate, and it's 70 concentration, and we've got a change in time is 20, and so we'll do the math at 3.5 moles per decimeter cube per second. Next, question 3, what does it want? It wants us to use the graph to find the average rate of reaction in the first 5 seconds. So you find the first 5 seconds there. Stick in the change in y, which is, as you can see, it's like 35 moles per decimeter cubed. The change in time is obviously 5 seconds. Do the math. You've got 7 moles per decimeter cubed per second. Next question. Use the graph to find the average rate of reaction between 10 and 15 seconds. So, sorry. So, we can put those in there. We've got it at 10 seconds. We've got it at 15 seconds. We need to find out that slope, change in y over change in x. Use a little ruler to find out, just to make sure we're accurate. And conveniently, it ends up at exactly 10 moles per decimeter cubed over 5. And so we got 2 moles per decimeter cubed per second there. And next, we want to use the graph to find the instantaneous rate at 9 seconds. So you find 9 seconds, which is there. And then this time, you make a tangent to it at exactly 9 seconds. Then you work out the rate, or you work out the slope of that tangent, and it gives you the rate of the instantaneous rate of reaction at that particular point. Okay, and that's the end of this presentation. Splendid.